Our first speaker that we have in the session this morning, Keith Berns, Debbie Absher, and I were lucky enough to see this presentation, I think, in Indianapolis. And Keith is the co-owner of Green Cover Seed. Some of you guys might be familiar with a calculator that's available on their website that I can't remember the name of right now. But he's just a really good teacher and is able to put this soil health idea together in a way that's really accessible to everybody. So with that, I'm going to invite Keith up to the podium here and let him talk about Carbonomics.
So it's a pleasure to be here in Delaware again. I was here a couple years ago. And we're excited to be able to come back and to share a little bit more about what we do. Just a little bit of background before I jump in here. We have a family farm in Nebraska, long ways from here. But the principles that we're going to be talking about are similar, and they will work everywhere. The practices that you need to use to put them to work are going to be different. But in Nebraska, we've been no-tilling there for more than 30 years. We're about half dry land, half irrigated. We farm about 2,500 acres. Fairly typical rotation in our area, corn and soybeans, of course, and then on the dry land, the cereals added into that. But since we started down this path to soil health, we've tried to diversify more, so now we're growing crops like rye and triticale, oats, barley, vetch, sunflowers, buckwheat, things like that, which of course gets all your neighbors going, what the heck are they doing now? Which is always fun. That's what we like to try to do. In 2009, 11 years ago, we started a cover crop seed business that grew out of an experiment that we did with this little SARE grant, and we just saw the power and the value and the benefits of diverse cover crop mixes. So this is Green Cover Seed. We started this in 2009. And just to give you an indication of how fast the whole soil health movement has really grown, in 2009 when we started, we sold enough seed to cover about 1,000 acres, with quite a bit of that being our own ground. So we didn't make a lot of big sales that first year. This year in 2020, we expect that we'll surpass the 1 million acre mark of how much seed that we move out the door. So it just gives you an indication of how fast things have grown. One of the great things that we've been able to do since starting Green Cover Seed is we've been able to meet a lot of really smart people, a lot of great people, be a part of a lot of projects. I wanted to just show you this one. If you have not seen the Living Soil film, I would encourage you to do so. This is completely free. It's online. Soil Health Institute funded this. livingsoilfilm.com. You can watch it. It's about 60 minutes long. It's a really, really good documentary. Is Rob Myers here yet? I don't know if Rob's going to be speaking later this afternoon. His daughter actually was the filmmaker on this. Did a fantastic job. It's very, very professionally done. But what they did is they went around and they interviewed and they got video of a number of different farmers across the country, large farmers, small farmers, organic farmers, non-organic, and they just put together this really good documentary about the soil and about the living soil. And one of the things that they wanted to demonstrate, of course, one of the principles of soil health is to have a living root growing as often as possible. So you can see from the picture here, this is a picture from our field with the air seeder out in the field as the combine is picking corn, and they wanted to get that whole picture of us going out to the field and everything. So I just wanted to show you one little clip here, and go ahead and play that. So they said, yeah, we're going to come out, we're going to film this. I said, oh, great. So I had the hired man go hook up the air seeder to the tractor. And so, I hopped in and was taking off. And, it was a gorgeous day in October. And as I was shifting up and getting faster and faster with the tractor, I was thinking, man, this is great. This is going to be really good exposure. This is could be in a movie theater someday. We're going to be movie stars. And just about the time when you think, man, things just couldn't get any better than this. God kind of has a way of humbling you. So I'm guessing that if you're a farmer, you've done something stupid like this, but you probably don't have it captured on high definition drone footage like I do. Okay, so this morning I want to talk to you about this concept that I call Carbonomics, and what I want to do is I want to try to explain or describe in a big picture way what's going on in the soil in a little bit different format by comparing it to the economy of a country. And I have to give credit to Dr. Christine Nichols right here, because this whole concept kind of stemmed out of a conversation we had in Colorado. Gosh, I don't know what that was, 6-7 years ago probably. But we were kind of talking about this and how, plants use carbon as almost like money. And that kind of just bounced around in my head for a while, and it finally kind of came out, and I put this presentation together, and it really helps people understand what's going on in the soil, because it frames it in a completely different manner than what you may be used to, and it frames it in a manner that even non-farmers can get a pretty good grasp on what's going on. So bear with me. We got a lot of information to cover. We're going to go pretty quickly here. But if you remember, maybe you don't, from high school or college economics class, there are several keys to a healthy economy: supply, demand, currency, capital, energy and resources, infrastructure, defense and protection. And I'm going to show you how these exact same things are keys to having a healthy soil. Not only they are important for the economy of a country, they're extremely critical for what's going on in our soil. And when we look at our soil and how this whole economy is formed and how it functions, the first thing that we have to understand and recognize is that it's all based on the sun. It's solar energy. We are a solar-powered economy, a solar-powered industry. And then the three main players within the economy that we work in are the soil. That's pretty obvious. The plants, of course we know that, because that's what we're harvesting. But the one that gets kind of ignored oftentimes are the animals. And when I say animals, it does include larger animals like livestock. I'm not going to be talking about them very much in this talk. I just simply do not have time. They're important. But what I'm going to be focused on mainly is the small critters, the biology. And then all the mistakes that I make, Dr. Nichols is going to come up after me and clean me up here. So it's always good to have a smart person talking after you, because they can correct what you say. But we're going to be talking about how important the biological aspect is to making this economy work the way that it was created to work. So first of all, on the supply side, plants are producing or supplying carbon. And we start with supply, because you can't have an economy if you don't have something to sell. If you don't have something that you're making to offer out to other people, it's impossible to have an economy. So in the soil economy, plants are producing carbon. You all know this. This is photosynthesis. This is the most important chemical formula in the world. CO2 plus H2O, with the energy and the power of the sun happening inside these little chlorophyll cells, these chloroplasts inside the plant. And it's turning that into C6H12O6, which is glucose, which is a very simple carbohydrate sugar, and oxygen. Okay? It looks very simple, but it's the basis of all of our life. And nobody else can do this. Animals can't do this. We can't do this. Plants do this. This is their thing. This is what they produce. They supply carbon to the system. The soil is providing nutrients through minerals. If you look at this chart, just ignore nitrogen right now, because that's not coming from the soil. We'll talk about that later. But all of these other ones, potassium and phosphorus and calcium and magnesium and iron and boron, the list goes on and on. These are minerals that our soils are made up of. They provide these nutrients, these minerals to the system. That's their contribution. They're also providing a habitat for roots and biology, because plants have to have a place for their roots to go, and the biology has to have a place to live. So it is actually a habitat. And if we would think of soil more as a habitat, I think we would treat it more differently than if we just thought of it as a chemistry set. But it also provides water storage, and soil providing water storage is a huge, huge part of this, and it's often overlooked. I was at a conference earlier this year, and I heard somebody talking about when somebody asked them how much rain they get, and maybe that's not such a big deal here, but where we're at in Nebraska, that's, anytime it rains a little bit, people are always asking, well, how much rain did you get? And, we measure it in hundredths of an inch, because sometimes that's all you get. But his answer, I love his answer. I'm going to start using this. He says, I always say, all of it. I got all of it. And you can't say that unless you have great infiltration and have the ability to store it. Okay, so remember that. Next time somebody asks you how much rain you got, you just say, all of it. I got it all. And I can store it. And you can't do that unless you've got good, healthy, functioning soils with good organic matter levels. And we're going to look at how that works here in a little bit. And then thirdly, the biology, they're producing, this is what they're supplying to the economy. They're producing nutrients through fixation, We'll look at that process and how that works. They're making nutrients available through nutrient cycling and nutrient availability, and they're also providing a lot of defense and protective mechanisms, because this economy that we're developing is always going to be under attack by things that want to consume without actually producing. And so we have to defend and we have to protect against that. Okay, on the demand side, plants need nutrients and water. Plants need services. They need to be protected and supported. No big surprises there. So supply and demand are the basis of the economy. So on the demand side, that's what plants need. Soil needs carbon. Soils do not function properly if they don't have carbon. The more carbon they have, the better they can function. It's just that simple. But they also need services. They have to be protected, because your soil can do some pretty amazing things, but it cannot protect itself. And that's why on the first slide that I showed, I should have pointed that out, I had that picture of our corn coming up, and it looks like I went out there and mulched a garden. But I didn't. The whole field looked like that because we had wheat stubble from the previous year, and then we planted a cover crop into that. So we had tons and tons of great residue. Our goal is to never see our soil on our farm unless I go looking for it. I don't want to see my soil on accident. It has to be on purpose. I want to have to scrape away that residue. I need to have that protection, because if I can see my soil, it can wash away or it can blow away, and we don't want that. And then lastly, on the demand side, the biology, they're living organisms, so they need food and they need habitat. If you give them room and board, they are happy to work for that, and they will do some pretty amazing, pretty phenomenal things, and they work really, really cheap. And so in a strong human economy, kind of like what we've got going on right now, the best indicator of a strong economy is a low unemployment rate, because it means everybody's actively engaged in making a contribution to the system, to the economy. You've got everybody participating, everybody is contributing, and it's the same way in our soil. Our soil economy is strongest when everybody is producing and consuming, including and especially the biology. And diversity is very important. I can't stress that enough, is that we don't want just one kind of plant, we don't want just one kind of biology. We need diversity, and that's important in a human economy as well as in our soil and plant economy, because if we are focused and based just on one thing, it may go really, really great for a while, and then it's going to crash really, really big. And so when we farm in such a way, and well, I'll speak from my own experience, when we farm in such a way that we ignore the biology, we're maybe not out declaring war on our biology, but when we ignore the biology, it will eventually go away and become less and less effective. We essentially put it on the unemployment line, if you will, because we're not farming in such a way that makes it work. And so when we do that, when we have part of our economy that's not working, that's unemployed, we have to step in then with welfare payments. And so when I talk about agricultural welfare, I'm preaching to myself here as well. When we externally provide the plant with everything it needs from the outside, we weaken the economy. We essentially are taking the place of the biology, and we're replacing it with inputs through fertility inputs, crop protection inputs. And the reason that we do that is because when the biology is no longer doing its job, because it's no longer present, then our plants look sick, they look deficient, and so then we have to step in and we have to do this function from the outside that the system was created to do internally. And so that's a welfare payment. That's an outside injection of support into this economy, and it happens all the time. And I'm not up here saying that we should completely eliminate all inputs. I would love to, because we would be really profitable if we could do that. That's not necessarily the goal on our farm, is to just completely get rid of all of our inputs. Our goal is to reduce them as much as we can, get our economy working the way that it was created to work. I love what Abraham Lincoln, I don't know that he said this originally, but he quoted it. He says, "You cannot help men permanently by doing for them what they could and should do for themselves." And the reason I like this is because he's not saying we should never help people. We do need to help people, but we're not going to help them permanently if we continue to do things that they're capable of doing. And I think this applies to our soil, because we are not going to build and fix and regenerate and restore our soils if we continue to do for the system what the system could and should be doing for itself. We need to allow the system to work the way it was created to work, and specifically bring back the biology. And so on our farm, we don't have all the answers, but I think we're at least asking the right question now. And you have to have the right question before you can get to the right answer. And the question now that we ask ourselves when we make a decision about our farm is, how will this affect the biology? Again, we don't know all the answers. We're not that smart. We know lots of smart people, which is good. But we are at least asking the right question to seek that right answer. How will this affect the biology? Because it's that important. If you want to cut back on your inputs, your welfare payments, if you will, you have to get the biology back involved. Okay, that was supply and demand. Now, currency is important because it allows goods and services to be exchanged quickly and efficiently. You cannot have a strong economy unless you have a strong currency. And so in this soil system, in our plant economy, the currency is carbon, okay? CO2 plus H2O makes C6H12O6, which is that simple glucose sugar. It does not stay as a simple glucose sugar. That carbon molecule will be recombined into thousands and thousands of other carbon compounds inside that plant, but it becomes the currency that the plants use to purchase other things. So probably all of you have either heard from your parents growing up, or maybe you've actually told this to your own children, this saying, money doesn't grow on trees, okay? We've all heard that or said that, but think about it. In this economy, it literally does grow on trees and on corn plants and soybean plants and wheat. We are literally printing our own currency, and we're only limited by our capacity to crank up those printing presses to make more and more of it. So here's how it works. Plants are producing carbon through photosynthesis, but they're not using all of that carbon just to grow the plant. There is a significant portion of that. It could be as much as 40 to 50% of all the carbon that a plant makes through photosynthesis is leaked out through its root system. And I've got a great picture later on that's going to actually show this. But it's leaked out through the root system, and the biology come and they eat it, they consume it because it's their food source, it's what they live on. And in exchange for doing that, in exchange for picking up those carbon payments, they're providing services back to the plant. They're sourcing nutrients, they're delivering nutrients, they're protecting the plant. Because plants aren't stupid. In fact, plants are smarter than some people that I know, in the fact that if the plant is making that investment in that carbon, if they're making those payments out into the soil, and they're not getting anything in return, no return on investment, guess what? They stop spending money. They'll stop doing that if there's no biology there to deliver those services back. Unlike some people I know, they continue to spend money even though they're not getting any return on investment. I may or may not be talking about myself, but that's how it works. The plants are paying with the carbon. The biology is consuming it, they're living on it, they're growing their populations, but they have to deliver something in return or the plant is going to shut them off. No such thing as a free lunch when it comes to this economy. Carbon is hugely important. It's essential to all life forms. You and I were 19% carbon. We can form over 10 million different carbon compounds. It's the most important but the most overlooked of all plant nutrients. How many of you have ever sat down with your crop consultant and said, let's make a carbon plan for our next crop? Now, you talk about nitrogen and phosphorus, potassium, all these other things, but we never talk about a carbon plan for our next crop. But it's the number one thing that plants need. And we should think about it more. Carbon is the main food source for soil biology. When we have more carbon in the soil, it normalizes our soil pH. It gives us a big buffer there, whether we're high or we're low. It increases our cation exchange capacity. It increases the availability of these essential nutrients that plants need, and it can help reduce the availability of things that can build up to toxic levels like sodium and aluminum. It can, as a currency, it's perfect because you can collect it through photosynthesis. You can spend it by trading it to soil organisms. That's what the plants are doing. You can save it by putting it into soil organic matter, which we're going to look at next. And it's desired by all members of the economy. Everybody in this economy has to have carbon. They want it, which makes it the perfect currency. It has different states, just like a currency needs to have. You have the gaseous form of CO2 that's in the atmosphere all around us. You have the liquid form of carbon that's moving up and down through the plant and through the soils as a liquid. And then, of course, when that is consumed by the biology, it's put into a solid form of carbon. And so it can go from one state to another very, very quickly, very, very efficiently. And it's just a perfect currency that drives this whole system. And then when we have excess currency, you can turn that into capital. And capital, that's another economic principle. It's just simply stored or saved currency. And it can be the form of a savings account or savings bonds or investments into equipment or into land, but it's simply accumulated currency. And in our system, in our soil and plant system, our capital is our organic matter because that's our stored carbon, that's the long-term carbon. Now we could spend the rest of the day, the rest of the week, just simply talking about how important soil organic matter is. We don't have time for that. I think we can all agree that it's very, very important. Here's a slide from Dr. Jennifer Moore-Kucherev with NRCS, where she talks about all the different functions of soil organic matter and how important it is for the functioning of a soil. For that healthy soil definition, you have to have organic matter. And so that's the capital, that's the stored benefits. And here's why it is so important, because one of the reasons the United States has had such a strong economy for such a long period of time is because we've had access to a lot of capital. We've been able to grow green cover seed from basically nothing to this large business with 40 employees and servicing over 1 million acres of cover crops in a relatively short period of time because we had access to lots of capital. We could go out and we could borrow money at a very reasonable rate. So it's helped make us productive and stable and resilient and efficient. And it's the same way in our soils. We have soils that range all the way from the new soils that we've just started farming, maybe 1.5, 1.6%, all the way up to some soils that haven't been farmed very long. They've been grass most of their life, and now we are farming them. You know, those are almost 5% organic matter. Well, the 5% organic matter soils are always the most productive, the most stable, the most resilient, and the most efficient. They're the last ones to show signs of a drought, the last ones to show signs of diseases or insects, because they have that high organic matter in there. It's that capital that the system can pull on in stressful or tough times. But just like in our human economy, you can't build your savings account if you're not earning more money than you spend. Okay, that's just a financial principle that applies to everybody except governments, I think. You can't build your savings unless you're bringing in more than what's going out. And it's the same way in our soils. You can't increase soil organic matter levels unless you're bringing more carbon into the system than what you're sending away. And how do we send carbon away out of our system? Well, it takes the form of anything that you load in a truck and you haul off, whether it's corn or pumpkins or hay. That's all carbon exports off of our soil. But we also lose carbon out of our soil every time we do a tillage pass. It oxidizes the organic matter and sends it back to the atmosphere as CO2. And even as our residue is breaking down, there's a percentage of that carbon that returns to the atmosphere as CO2. And that's okay. That's part of the carbon cycle. It's natural. But if we don't have more coming in than we have going out, our savings account gets depleted, and that's what's happened. That's what's happened in soils all across the world, and here in Delaware, it happens in Nebraska. When we are losing carbon, we are losing organic matter. And so if we're going to rebuild our soils, we first of all have to get more carbon coming into the system than what's going out. And that's why cover crops are so very important. Cover crops are hugely important to a system because they're bringing carbon into our system, and we're not exporting it back out because I'm not going out there and harvesting it. I'm not going out there and I'm haying it. Now, I may graze them, and if I do properly manage grazing, that can be a good thing because 80% of what goes in a cow is coming right back out the other end. So that's a good thing. It helps cycle things quicker and faster. But cover crops put much, much more carbon into the soil than what you lose. And so I'm almost to the point now where I tell people, look, if you don't put cover crops into your rotation somehow, it's going to be extremely difficult for you to increase your soil organic matter levels. And we see that on our own farm. You can to a point, but you'll stall out, and then you need that additional input of cover crops. Okay. Energy and resources. This is the next economic category. I told you early on that our plant economy is powered by the sun. And think about how cool that is. Think about how great this is. Tell me one other industry where all of our energy, well, not all of our energy, but the base of our energy is free. And it's constant, and it's unlimited. You get a new supply every day, and you don't have to pay a thing for it. The government hasn't figured out how to tax us on sunshine yet. Fortunately, I don't want to give anybody any ideas, but It is a constant, unlimited, and can be collected source of energy. All we have to do is collect it. So as farmers, really what we're doing is we're capturing solar energy and we're turning it into something that has value, something that we can sell. And so we just have to put solar collectors out. And for farmers, it's much easier than for other people. All we have to do is plant seeds and out pop these little solar collectors called leaves. And we start turning that solar energy into that chemical energy through photosynthesis. And then it eventually gets turned into biological energy. And that becomes the source of energy to power the entire world, if you think about it. So solar energy is there for the taking. We just have to collect it. And a healthy soil economy should not need significant purchased energy inputs. And I say that because many of our soils across this country have been built by these plants, these tall grass, mixed grass, short grass prairies, growing over the course of thousands and thousands of years, have built these really deep, rich, dark soils with no outside energy inputs other than the input of the sun. Some of you may have heard of Dakota Lakes, Dr. Dwayne Beck up in Pierre, South Dakota. He's got a really cool research farm up there. Their goal for that research farm is to be fossil fuel neutral by 2026, okay? So in 6 years, they'll be fossil fuel neutral, and they're gonna be doing that because they're growing oilseed crops like sunflower and flax and canola, and they can crush the oil out of that, which becomes an energy source. But they're also doing it by drastically reducing their other inputs. They're cutting back on how much welfare payments they're giving to their system, and that's a really cool thing. They're doing it to prove that it can be done so that the rest of us can try to figure out how we can get closer to that. But if you were to look at the energy budget of your farm, I know when we look at the energy budget of our farm, our number one energy use, it's not diesel fuel, it's not electricity, it's not propane or natural gas. Our number one energy expense on our farm is nitrogen fertilizer. And let me show you why that is here. So first of all, we're shifting over to the resources side now. So carbon is the number one resource that plants need. We've talked about how plants can get carbon out of the atmosphere, but a lot of times our plants, and I don't pretend to be this smart, so we can ask Christine this later, but I think a lot of times our plants are limited on their growth because they can't get enough CO2. That's the limiting factor. So when we are farming in such a system where we have residue, we have good residue from a cover crop or from a previous crop on the surface of the soil when our next crop is growing, as that residue is breaking down, it releases CO2. And if we have another growing plant there, that growing plant is going to capture that CO2 before it ever gets to the atmosphere. It's capturing it right out of that decomposing residue. So it's kind of a catch and release type deal. We're catching the CO2, and then as it's being released, we can capture it. So we can get carbon from more than one place. But look at this chart of the atmosphere. This is a pie chart of the atmosphere. The little tiny pink sliver up at the top, you can probably barely see it, but there's a little tiny pink sliver at the top. That's how much CO2 is in the atmosphere. 0.04% of our atmosphere, give or take, is carbon, CO2. That's not very much, but yet our plants are pulling the majority of the carbon that they need to grow out of that tiny little sliver of atmosphere. The big blue chunk, 78% of our atmosphere is nitrogen. And we spend $0, for most of us anyway, spend $0 putting carbon into our system, and we spend billions of dollars putting nitrogen into our system. But look at the atmosphere. Why is that? Well, there's good news and there's bad news, okay? The good news is we're not dead, okay? Which is always good news. But atmospheric nitrogen is held as dinitrogen. It's two nitrogen molecules bonded very, very tightly together. There's 3 sets of covalent bonds that hold those two nitrogen molecules together, so they're bonded to each other, which renders them inert. So as I breathe, I'm taking in 78% nitrogen. Does nothing to me because it's inert. It's bonded to each other, can't attach anything inside me. It goes right back out. So that's the good news, is that we're not dead, because if you've ever had a whiff of anhydrous ammonia or ammonia out of a Clorox jug or anything like that, you know what nitrogen that's not in inert dinitrogen form can do to the insides of you. I mean, it would just melt us down and there'd be nothing left. Okay, so none of this would really matter. So the good news is we're not dead. The bad news is just as it's inert to our bodies, it's completely inert to plants as well. So when your plant is taking in the atmosphere to get that CO2 and it's stripping off those carbon molecules, it's taking in 78% nitrogen as well. It can do absolutely nothing with that nitrogen because it's held together as dinitrogen. It has to just spit it right back out. It can do nothing with that nitrogen. In order for the plant to get nitrogen, it has to be in a form that you have to, first of all, pull those two nitrogen molecules apart, and then you combine it with hydrogen and oxygen and different things to make these plant available forms. So we call that fixing or making it available. And so there were some scientists back in the late 1800s and early 1900s, they developed a process of figuring out how to do this. And actually, they ramped this process up, some during World War I, but a lot during World War II. They built these big nitrogen-producing factories. They didn't build it for agriculture. They built it for making bombs. Because when you can pull that nitrogen molecule apart and then recombine it with different things, it becomes a very, very powerful explosive. And some of you are old enough, like me, to remember 26 years ago, the Oklahoma City Federal Building bombing, where Timothy McVeigh blew up that entire federal building, the huge concrete structure. What bomb did he use? It was a rental truck full of ammonium nitrate. It was fertilizer. Hugely powerful, hugely explosive. It was the bomb-making material of choice in the world wars. And after the wars were over, they kept these things going to make nitrogen now for agricultural use, okay? And that kind of started the beginning of the welfare state, if you will, of modern-day agriculture. It has allowed us to be very productive, but that productivity has come at a great cost. So when you are paying for nitrogen, okay, you're not actually paying for the nitrogen, because above every acre of crop ground in Delaware, Maryland, Virginia, Nebraska, above every acre of crop ground in this country, in this world, there are 30,000 tons of nitrogen. You've got 30,000 tons of nitrogen above every acre of crop ground that you have. You don't have to pay for nitrogen. It's there. You have to pay for the energy that it takes to pull that nitrogen molecule apart, put it into a form that your plants can use. That's what you're paying for. So that's why I say if you look at your energy budget, the number one expense that most of us have is nitrogen fertilizer, because it's a very energy intensive process and it takes a lot of money. But thankfully, what takes man billions of dollars in these big fancy factories to do, God has created these tiny little bacteria, these little rhizobia bacteria that do the exact same thing. Inside these rhizobia bacteria, they form these colonies that you see right here. They form as nodules on legume plants. They are pulling that nitrogen molecule apart. They're pulling that apart. They're combining it with hydrogen and oxygen and turning it into plant available forms, which is really, really cool. And that's why legumes don't need to be fertilized with nitrogen fertilizer, but it's not because the legume plants can do anything with nitrogen. So don't ever tell people, well, I'm growing alfalfa, it can make its own nitrogen. No, it can't. No, it can't. It's the bacteria that's doing it. And the bacteria don't do it for free. They're only going to do it if they get paid. Because as cool as breaking that dinitrogen molecule apart is, and that's a superpower that rhizobia have, they can't eat nitrogen. They have to have carbon in order to survive and to grow and to build these big colonies. So they will not do this if the plant is not willing to pay cash, currency, carbon, in order for this to happen. Now, it's not just limited to legumes, though. There are other critters out there like Azospirillum and Zotobacter, and they're discovering new ones all the time. There's lots of other free-living nitrogen fixers. So these are single-celled organisms. They don't form these colonies like they do on legume plants, but they're doing the same thing. They can pull that dinitrogen molecule apart. They can combine it with hydrogen and oxygen, make it into a plant available form, and then they can essentially kind of sell this to the highest bidder, if you will. They can trade this to plants in order to get that carbon root exudate back, because that's how the economy works. And you know, this should be really good news for us, right? Because now if we want to grow 250 bushel corn crop, all we got to do is just dump a whole bunch of these guys out there and we should be ready to go, right? How comes we're not doing that? Well, here's the reason we're not doing that. These guys are incredibly productive. If I'm growing 70 bushel soybeans in Nebraska, That is the equivalent of having to have about 350 pounds of nitrogen. How many of us would grow soybeans if we had to put 350 pounds of nitrogen out there? None of us would. You couldn't afford it. It wouldn't make any sense. But these guys, rhizobia bacteria, can produce 300 to 400 pounds per acre of nitrogen in about 60 days. Very, very productive, extremely efficient, because they form these big colonies. They're not doing it on their own. They form these big manufacturing facilities, and they nodulate on the roots of these plants, and they can be very, very powerful. These guys don't do that. They're single-celled organisms. They don't form these colonies. They're not nearly as productive. They're producing probably 30 to 50 pounds of nitrogen, not in 60 days, but per year. Okay, so is 30 to 50 pounds of nitrogen going to get you a 250 bushel corn crop? Not by itself, it can be part of it. So this isn't just the only answer that we need for high productivity farming, but think about what 30 to 50 pounds of nitrogen would do for a cover crop, or for a forage crop, or for just native vegetation. If you think about it, when you drive down the highways and you look in the ditches and the medians and you see that grass growing out there, how many times have you ever seen that look nitrogen deficient? It never looks nitrogen. It may be dry, it may be other things, but it's never nitrogen deficient, and it's not because there's a bunch of legumes growing out there to produce nitrogen for the system. And I don't think the highway system is out there fertilizing those at night when we're not looking, although sometimes you wonder, but I don't think that's happening either. The reason that those grasslands and our native grasslands never look nitrogen deficient is because we have colonization of these little critters like this, and they're producing 30 to 50 pounds of nitrogen per year, and that is sufficient to keep a closed system, because we're not hauling hay off of that all the time, so that nitrogen that they produce is cycling, and it's always there, and it's cycling through the system. So as cool as all this is, remember, they're not going to do this unless the plant is willing to pay for those services with that carbon currency that they're creating through photosynthesis. And this is also not going to happen if there's excess nitrogen in the soil. So you really have to manage your system well if you're going to take advantage of these biological nitrogen fixers, because if you want to get rid of these things and make them not work, the best thing you can do is to put a whole bunch of synthetic nitrogen out there. Because again, plants aren't stupid. They're not going to pay for something that they can get for free. Okay, so if you're giving them free nitrogen out there, they're not going to be putting those carbon payments out there to try to get this service from the system. Okay, so we talked about carbon, we talked about nitrogen. Now, all these other mineral resources that I talked about and I told you earlier, these are in the soil: the phosphorus, the potassium, the calcium, magnesium. Our soils are made up of these minerals, but plants were never designed to pull those minerals directly from the soil. Much of the mineral resources in our soils are not available to plants, just like the nitrogen in the atmosphere are not available to plants. Same solution, you have to go through the little guys to get it. So the solution, if we want to get these mineral resources from within our economy, we have to employ tiny little miners to extract the nutrients from the soil. I love this article. This is from Scientific American a few years ago. It says, mycorrhiza fungi run the largest mining operation in the world. And you think about mining, when I think about mining, I think about these giant trucks and these giant front end loaders and just huge, huge scale of what's happening. This is happening at a microscopic level. You don't even see this happening unless you have a microscope to see it. But they call it the largest mining operation in the world. And I don't mind telling you how nervous I am telling this part with one of the world's foremost experts on this subject sitting right here. I feel like when I was a teacher and my principal came into the room for the first time. So you can correct me later if I'm wrong. But they're saying mycorrhiza run the largest mining operation in the world. And look at this picture to the right. This is a piece of feldspar, highly magnified. Just think of it as a tiny little grain of sand, okay? And there's minerals in that sand. That's what it's made up of, is all these minerals. And you see those little brown hollow shafts cut into that. Those are actually hollowed out mine shafts, if you will, that the mycorrhiza, through a combination of these different chemicals that they exude and also different bacteria that they will grow out on the tips of their hyphae, can actually dissolve that solid mineral material and bring it back to the plants. And as cool as that is, that's a great superpower to have. They can't live on that. They can't eat those liquid minerals. They have to have carbon. So again, they're not going to do this unless the plant is willing to pay money to get those services. So here's what they look like. This is a picture of a highly magnified plant root. The little round black things that you see in there, those are called the arbuscles. That's kind of the nucleus or the headquarters. And then you'll see the hyphae growing out through the cell wall, the root wall, and that's what goes out into the soil and it explores it and it brings these nutrients back in. And the author of this article, Jennifer Fraser, she says, mycorrhiza mine for all the basic things, but also the hard to come by things like zinc and copper and manganese, which plants need to survive. And she says, oddly enough, many of our soils are rich in important nutrients, but they're locked up in a physical form, which makes them unavailable to most plants. And that's exactly right. Your soils have many of the nutrients that your plants need, but unless you have biology there to unlock it, they can't get it. And what you see on a soil test is not telling you what you have in your soil, it's telling you what you have in your soil that's available to plants. And that's why once you shift to a regenerative biological type farming system, traditional soil tests no longer are adequate to tell you what you've got out there because you have access to lots more once you have the biology there and working. Okay. Next economic principle is infrastructure. Infrastructure is equipment and structures like roads and bridges, things that you need for a country, region to function properly. We know that the two most important infrastructures are transportation and communication. We know this because in times of war, this is what you do to your enemy, is you try to destroy their infrastructure. You blow up their bridges, their railroads, their airports. You would try to, nowadays you try to take out an internet communication center. I mean, think about what the economy of a country, the United States, think about what our economy would do if you could no longer travel or you could no longer communicate. It would literally bring this country, it would grind it to a halt, and you could easily come in and take over. So as I was thinking about the importance of transportation infrastructure and thinking about the United States and the strong economy we have, and I've done some international travel, not a lot, but some, and I've seen other places that don't have infrastructure like we have. One of the things that's made us such an economic powerhouse is we have a very good, robust transportation infrastructure. So this is the interstate highway system, which is large roads, multi-lane roads that move a large amount of goods and services. Although I found out here in your area, you've got a lot more goods and services to push through your roads than we've got in Nebraska. But these are large corridors that can move a lot of things back and forth, which is great. But I'm here in Nebraska, so I'm down here on the Kansas border, about right there is where we live. So I've got to go 50 miles to get to Interstate 80. I've got to go about 90 miles to get down to Interstate 70. That interstate does me no good if I can't get to it. I have to get to the interstate before I can take advantage of it. So what really makes us a powerful transportation infrastructure is the other highways. It's the feeder roads. And so within the United States, there's not a very large population area that doesn't live too far away from a good paved road that takes you to a better paved road that will eventually get you to an interstate to allow you to transport your goods and services. Same thing is happening in our soil. This is the same thing. These are some very famous pictures from Mycorrhizal Applications, a company that makes a mycorrhizal inoculant. The picture on the left is a plant with no mycorrhiza. So this is just the roots of this plant. Think of that as the interstate highway systems, large corridors that we can move large amounts of goods and services back and forth. But look at how much the soil it's touching. These roots can only get what they're touching, okay? So they can move a lot of stuff, but it doesn't do that plant any good if it's not touching very much. There's not anything there to move. It'd be like an interstate with no highways coming to it. There'd be very little traffic on it. The picture on the right is the same plant, the same roots, but now this is colonized with mycorrhiza fungi. Now look at the hyphal network, this spiderweb network of hyphae coming out from the mycorrhiza, and it's exploring all that soil. These are like the highways that are bringing everything to the interstate system, and now that plant can really, really function because now that plant can access water, it can access nutrients from a large amount of the soil around it, and that can be a very, very healthy plant. Again, another picture of mycorrhiza. They can help transport phosphorus, which is one of the most difficult ones to access. And I know that you guys don't necessarily have phosphorus issues here, just in visiting with some of the farmers. We need to get our soils together because you're talking 300 to 500 on your phosphorus test. In Nebraska, on our soils, we have 3 to 5. not 100, 3 to 5. So phosphorus is a pretty big deal for us, but it can also bring in other things like nitrogen, potassium, calcium, magnesium, all these different things. And in times of dry weather or in drought, mycorrhiza also can bring in water. They can actually be a water collection system. So if you really want to have a drought-tolerant crop, we don't just need to look at genetic technology, we need to look at this biology, because when we can colonize a plant with mycorrhiza, we make it much, much more drought tolerant. But it's not just mycorrhiza that are doing this transportation within our soil. Earthworms are also a huge, huge transportation infrastructure because they're burrowing up and down, they're leaving these channels behind, and it's a huge way to transport water and oxygen and surface carbon residue, and it's actually even moving other biology from one place to another throughout the system. So they're kind of like the public transit system of an economy, if you will. And people a lot of times ask me what they should do for a biological test for their soil. First question I always ask them is, do you have earthworms? Because if you don't have earthworms, if you're not out there digging in your soil and you don't see worms or you don't see evidence of worms where they've been, because if it's dry, you're not going to find them, they're going to be down deeper. But if you don't at least see that they've been there and they've been working, don't waste your money on testing for other biology. Because if you don't have earthworms, your soil sucks. You've got a lot of work to do before you have earned the right to even start testing for other biological activity, because the earthworms are the one thing that we can see, and they're the bellwether of whether or not your soil is starting to improve. So once you start seeing earthworms and you start seeing that activity and you see all these wonderful channels, because that's a huge increase to your infiltration and your oxygen exchange, once you start seeing that, now you can start talking about what other types of biological testing do we want to do, because you can't see mycorrhiza. You can't see those, all the Zotobacter and Azospirillum. You have to test for those, but we can see earthworms. And that's why if you don't have a shovel and you're not digging in your soils, then you really are just kind of guessing at whether you're making improvements or not. So make sure you have a shovel, make sure you're digging, make sure you're monitoring those earthworm populations, because they're a huge benefit in the transportation infrastructure. And then the other infrastructure that's super important is communication, because think about it, how do the mycorrhiza and the other biology know what a plant needs? Because some of these nutrients, take boron for example, plants need boron but at very low levels. And if they get too much of it, they'll die. It can kill them. So if mycorrhiza aren't bringing the right stuff, they could actually bring too much of the wrong thing to a plant, and they could actually kill their host plant. So somehow the plant has to be telling the biology, the mycorrhiza and the other organisms, it has to tell them, what do I need? And they have to communicate, and the way that they communicate that is by different types of liquid root exudates. Remember, from photosynthesis, it's making glucose, C6H12O6. It does not stay in glucose. That carbon molecule gets recombined into thousands of other different carbon compounds, and the different compounds that are leaking out into the soil structure, into that rhizosphere, is communicating to the biology what the plant wants. And so I'm not going to go into the science of it, mostly because I don't have any idea what I'm talking about. But basically, the different compounds are signaling for different things that the plant needs. Here's that picture I was telling you about. This is one of the coolest pictures I've ever seen. This picture was taken by my friend Jimmy Emmons. Some of you may have heard him talk before. Oh, he was here last year, wasn't he? Jimmy was here last year. Did he show this picture? Okay, if he showed it, well, you can look at this every day. He took this with his iPhone, first of all. So if you like taking cool pictures of your soil, spend $150, get a little attachment. It's called a ProScope. It goes right over your iPhone lens, and you can zoom way in, and you can kind of have a little amateur microscope just with your iPhone. So he took this. Now, this is not mycorrhiza, okay? It's not highly magnified enough to see this. This is just a plant root. This is cereal rye cover crop plant root. And what you see coming off that plant root are the little root hairs. But what I want you to notice is all the little droplets of liquid. See all those little liquid droplets on those root hairs? That's the liquid carbon that plant is exuding out into the soil to feed the biology. That's made up of carbohydrates and sugars and proteins and fats and lipids and oils, all number of different carbon compounds to communicate to the biology what that plant is wanting. Now, here's how he was able to take this, because I've never seen anything quite like this. Because think about it, when you pull a plant up out of the soil, what happens to all those tiny little root hairs? Well, yeah, they just pull off. They slough off. They're very, very fragile. You hardly ever see those. So if you were to carefully dig it up and do a really careful root wash and gently wash the soil away, you could probably preserve a lot of those root hairs. But in the process of washing that soil off, what happens to all those little droplets of liquid? Well, you're flushing those right away. So you almost never see this. The reason he was able to take this root was not growing in the soil. This root was growing horizontally through a worm channel in the soil like this, and this root was growing sideways like this. And so it was actually, what you see here is the cross-section of that cereal rye root that's growing through the diameter of a worm channel. So think about, what, a 1/16 of an inch, 1/8 of an inch at the most? That's what you're seeing here. It's highly magnified. And so you're seeing a very, very tiny cross-section, a 1/16 of an inch to an 1/8 of an inch of a cereal rye plant. But look at all the droplets of liquid. So now take that 1/16 of an inch and times it by how many yards of roots that one rye plant would have. Hundreds and hundreds, maybe thousands of yards. I don't even know what the number is. I need to find that out, because rye has one of the most massive root systems of anything you can plant. That's why it's such a powerful, powerful cover crop. And then take that times 1,000,000 rye plants per acre, and you can start to see how powerful these liquid carbon root exudates are in building the organic matter levels of your soil. Okay, Dr. Christine Jones, I heard her say that the carbon that goes into your soil through the liquid carbon root exudates through the plant, just like this, is 5 times more likely to end up being part of your organic matter than the carbon that's produced by the rest of that rye plant above the ground that dies and decomposes. 5 times more effective, the liquid carbon root exudates that go into the soil. So what's happening in the soil is more important than what's happening above the soil when it comes to this kind of a thing. And the cool thing about this is, this rye plant, this was not a 5-foot tall rye plant. Okay, this rye plant was probably 10 inches tall. So if you plant a cover crop and it doesn't get really big, that doesn't mean you didn't accomplish a lot by doing it, okay? It is starting to put these carbon root exudates in and build those biological communities much, much quicker. Okay, mycorrhiza can also interconnect root systems and allow them to signal through chemical signaling. There's been lots of experiments done on how plants can communicate through the root systems. They can also communicate through the air. This is an article in the Scientist magazine showing how plants, when they're connected, because the roots won't actually physically intersect, but 2 plant roots can be connected through mycorrhiza because it can colonize this root, and then the mycorrhiza become the conduit, which these roots can pass nutrients and water back and forth and also communicate. And plants can also communicate with each other through these volatile organic compounds through the air. And they can also signal in insects to help if they're under attack with an aphid or something, they can come in and rescue that plant from an aphid attack. So the last section that I'm going to talk about is defense and protection, because our economy needs to be protected from water, wind, heat, cold, compaction, all these different things. You know, we need water, but if we have too much or too little, it's a bad thing. So there's several basic things we can do on the protection side. The first one is just real simple. To me, it's the first principle of soil health. You have to keep it covered. You have to keep it covered. Rolf Derps, who's one of the godfathers of the soil health and no-till movement in South America, he says almost all advantages of the no-till system come from the permanent cover of the soil, and only a few come from not tilling the soil. Always aim at full soil cover, because folks, if you don't keep your soil covered, if it's bare and it's exposed for long periods of time, it doesn't really matter what else you do, because that soil is eventually going to wash away, or it's going to blow away, or it's going to get hot and cook and hard. Bad things happen when you can see soil, and so you got to keep it covered. Second line of defense is simply this whole plant signaling, the communication. I want to bring this back up. I have one more example because this is how plants in native, natural, healthy systems actually work. This is actually some research from the University of Delaware. This is a rockcress plant that they infected with a Pseudomonas syringae, a pathogen, and it turns this plant's leaves yellow, and then they turn black and they fall off and eventually kills the plant. The plant in the middle here is the same plant. It's infected with the same pathogen, okay? So Pseudomonas syringae is in that pot, but they also inoculated this plant with a beneficial bacteria called Bacillus subtilis. And what happens is when that plant senses that it's under attack from Pseudomonas syringae, it starts exuding all these liquid carbon root exudates that are communicating to Bacillus subtilis saying, hey, I'm under attack, I need help, and it puts out all this carbon as a food source, as this payment, and then Bacillus subtilis comes in, and bacteria can exponentially increase their population. So the populations of these good bacteria just explode, and that's what you see on the right. It's a magnified root of from this plant, and the Bacillus subtilis have grown to such a huge population that they've created this biological film that protects this plant's roots from infection from the pathogen. And so this is how things work in native healthy systems. The good biology outweighs the bad when you have a good balance. But when we go out and we kill everything off, then the good guys don't come back oftentimes as fast as the bad guys, and then we have to step in with our welfare payments. A third line of defense is just healthy plants are just naturally have better immune systems. This is some work from John Kemp. If you're interested in this, I would encourage you to look at his website, advancingecoag.com. But he's basically saying when you're stuck down at the simple photosynthetic level, your plants are subject to much attack. Insects love glucose. They can eat glucose all day long. They have very simple digestive systems. But once that glucose gets turned into proteins and lipids and these secondary metabolites, insects can't digest that. So the healthier your plants are, they will have a natural resistance to insects and diseases because those insects and diseases can't digest, they can't function within these complex compounds within a plant. Your plants never get there. They never can get to these complex compounds if your soil's not healthy. If your nutrition's not balanced, you'll never get there. A fourth line of defense is simply having additional symbiotic relationships. This is a picture of an endophyte fungus within a plant. It's different than mycorrhiza fungus. It's totally inside that plant root. It's giving that plant defensive mechanisms against both drought and disease, and in exchange, the plant is paying for it in carbon. And so there's lots of these symbiotic relationships between plants and organisms, and when we can encourage those and when we can exploit those, we can do that to our benefit. And then lastly, just having diversity, because most pathogens, most diseases, insects, they're only going to attack one or two things. So when you plant a cover crop, you want to try to have as much diversity out there as you can. And so if you're going to get something that looks like this, you have to plant seed that looks like that. Now that's not always possible, but when you have the opportunity to plant diversity, take advantage of that opportunity and get it in there. Okay, so that was Carbonomics. That's the keys to a healthy soil. I've just got a few quick takeaway points I'll go through real quickly to summarize this. Economies are interconnected and interdependent, and when you mess with one part of the economy, you mess with it all. So when you take the biology out of the system, and we don't do it on purpose, but when we're not farming for biology, it goes away. And so then that affects the other parts of the system, and they start to look sick, they start to look deficient, so then we have to step in with our welfare payments. So the second point is we need to reduce the amount of welfare that we're giving our economy, get everyone working the way God created them to work, especially the biology. Figure out how to get more biology back into your system. Number three, increase your cash flow of carbon currency. You know, I tell guys in my area when they're just growing corn and soybeans, they're less than 50% efficient at collecting solar energy and producing liquid carbon. Now, you guys are doing a better job planting cover crops here than we are in Nebraska. I've got a lot of work to do there yet, but you've got work to do here yet as well. Something green and growing all the time, because that is what increases your cash flow of that carbon. And then once we have that, once we have more carbon coming into the system, then we can save that, we can invest it, we can put it in a long-term storage, which is organic matter. And then when we do that, when you make those investments, don't come in and do any kind of unnecessary tillage or residue removal. Now I say unnecessary because I recognize if you're organic that there are some tillage that's necessary, just like if you're not organic, some herbicide applications are necessary. The goal is to reduce whichever one of those that you're doing. Get it down to the bare minimum levels. Number 5, take advantage of all the free tiny workers. They manufacture, they mine, they transport, they communicate, they protect, and they work really, really cheap. Number 6, build and do not destroy your infrastructure. You'll really see your economy grow. And then once you're farming in such a way for mycorrhiza and for earthworms, don't come in and do unnecessary things like this, because again, destroying the infrastructure is an act of war. So when you do this and it's not absolutely necessary, it's like you're declaring war on your soil. Number 7, protect your economy as soil armor. Again, it's hard to overstress how important it is to keep that soil covered because lots of bad things happen when it's bare. And finally, diversity is so very important for a healthy economy. Plants, roots, and soil animals. Get as much diversity into that system as you possibly can. Okay, you have seen on your tables, there's some of these soil health resource guides. Those are there for you to take. That's what we do. We printed 40,000 of these this year, and we're giving them all away for free. That's our contribution to education with soil health. Lots and lots of really good articles in here from some of the sharpest people in the soil health movement. So take that. If you want extra copies, check with Debbie at the end of the show. We can send more out. So my email is there if you have questions later on. I think we're going to have some question time later. So I'll be happy to help out with that too. Thank you so much for your attention. I know that we pushed through a lot. So thank you for your attention.